For centuries, humans have looked to the sky, wondering what lies beyond the stars. The invention of telescopes changed everything, but even the most advanced ground-based observatories are limited by Earth's atmosphere. The launch of the Hubble Space Telescope in 1990 was a revolution. Floating above the atmosphere, Hubble delivered breathtaking images of galaxies, nebulae, and star clusters. It showed us that the universe was more vast and beautiful than we had ever imagined. But Hubble had limits. It was designed to see mostly invisible and ultraviolet light, to study the earliest galaxies formed after the Big Bang, or to peer into dusty clouds where stars and planets are born. Astronomers needed to look in infrared light. Infrared wavelengths can penetrate cosmic dust and reveal objects invisible to Hubble. Thus was born the dream of a new observatory, one that would be larger, colder, and more powerful than anything built before. That dream became the James Webb Space Telescope, JWST, named after NASA Administrator James E. Webb, who led the agency during the Apollo era. The scale of ambition JWST is not just an upgrade, it is an entirely new class of telescope. Its primary mirror spans 6.5 meters, more than double the size of Hubble's. The mirror is composed of 18 hexagonal segments, each coated in a thin layer of gold, chosen for its ability to reflect infrared light. The mirror had to be lightweight yet strong enough to survive the extreme conditions of space. Engineers chose beryllium, a rare metal that remains stable even at extremely low temperatures. Behind this mirror lies a technological marvel, the sunshield. JWST must stay cold to detect faint infrared signals. To achieve this, it carries a 5-layer sunshield the size of a tennis court. Each layer is thinner than a human hair, and together they block heat from the sun, Earth, and Moon, allowing the telescope to chill to minus 233 degrees Celsius. A telescope far from home. Unlike Hubble, which orbits just 550 kilometers above Earth, JWST operates at the second Lagrange point, L2, a position 1.5 million kilometers away. Here, gravitational forces from Earth and the Sun balance out, allowing the telescope to hover in a stable orbit. At L2, JWST has a constant view of deep space, with Earth, Moon, and Sun always behind its shield. This location also keeps the telescope cold and stable, ideal for long observations of distant galaxies. But placing JWST so far away came with risks. Unlike Hubble, it cannot be repaired by astronauts. Every part of the mission had to work perfectly the first time. Engineers described the deployment as the most complex ever attempted. Over 344 potential single points of failure. If even one had gone wrong, the $10 billion observatory could have been lost forever. Why infrared matters? Infrared light is the key to unlocking the universe's secrets. The first galaxies are so far away that their light has been stretched, or redshifted, into infrared wavelengths by the expansion of the universe. Stars are born inside dense clouds of gas and dust, opaque in visible light but transparent in infrared. Exoplanet atmospheres reveal themselves through infrared spectroscopy, showing the chemical fingerprints of water, carbon dioxide, methane, and more. In other words, JWST is not just a telescope, it is a time machine, allowing us to see the universe as it was billions of years ago. The heart of the telescope, a giant golden mirror alone, isn't enough to revolutionize astronomy. The real power of JWST lies in its scientific instruments, the eyes and brains that turn faint starlight into data. Webb carries 4 primary instruments, each designed with unique abilities, working together to cover the broad infrared spectrum. NIRCam near-infrared camera NIRCam is the workhorse camera of JWST. Operating in near-infrared wavelengths from 0.6 to 5 microns, it captures razor-sharp images of stars, galaxies, and nebulae. It is sensitive enough to detect some of the faintest objects ever observed, galaxies formed only a few hundred million years after the Big Bang. NIRCam is also equipped with coronagraphs, devices that block out the blinding light of stars, allowing astronomers to study faint companions like exoplanets and dust disks. It was NIRCam that produced the now famous first deep-field images of JWST, showing thousands of galaxies packed into a tiny patch of sky. NIRSpec, near-infrared spectrograph. NIRCam is the eye, NIRSpec is the prism. It doesn't just take pictures, it splits light into its individual wavelengths, creating a spectrum. Every atom and molecule absorbs light at specific wavelengths, leaving behind fingerprints in the spectrum. By studying these fingerprints, scientists can determine what distant galaxies, stars, and exoplanets are made of. NIRSpec is revolutionary because it can study up to 100 targets at the same time. Imagine analyzing the atmospheres of dozens of galaxies or stars simultaneously. It's like having 100 telescopes in one. This instrument is key to understanding the chemistry of exoplanets and the evolution of galaxies. MIRI, mid-infrared instrument. While NIRCam and NIRSpec focus on shorter wavelengths, MIRI looks deeper into the infrared spectrum, from 5 to 28 microns. This region is crucial for studying cooler objects that don't shine brightly in visible light. MIRI can observe brown dwarfs, objects too big to be planets, but too small to ignite as stars. Protoplanetary disks, swirling clouds of dust and gas where planets are forming. Distant galaxies hidden behind thick veils of dust. Because mid-infrared light is essentially heat, MIRI must be cooled to an astonishing -266 degrees Celsius, only a few degrees above absolute zero. This is achieved with a special cryocooler, one of the most advanced ever flown in space. FGS NIRISS, Fine Guidance Sensor and Spectrograph. The Fine Guidance Sensor, FGS, ensures JWST can point with incredible precision. Even the slightest wobble would blur Webb's images. Thanks to FGS, JWST can lock onto its targets with accuracy finer than the width of a human hair at a distance of 1 kilometer. Combined with FGS is NIRISS, Near-Infrared Imager and Slitless Spectrograph, which adds extra capabilities. It's especially powerful for studying exoplanets using the transit method. When a planet passes in front of its star, NIRISS analyzes the starlight that filters through the planet's atmosphere, revealing its chemical makeup. Why multiple instruments matter. Each of these instruments covers a different slice of the infrared spectrum. Together, they allow JWST to create a complete picture of the universe, from the birth of stars and dusty nurseries to the atmospheres of distant worlds. This combination of imaging and spectroscopy, across a wide range of wavelengths, is what makes Webb not just a telescope, but the most powerful observatory ever built. The first light, unveiling the universe's dawn in July 2022, NASA revealed JWST's first images, and they changed astronomy overnight. The deep field image captured thousands of galaxies in a patch of sky, no larger than a grain of sand held at arm's length. Some of these galaxies were born only a few 100 million years after the Big Bang, further back in time than humanity had ever seen. Webb showed the universe not as static and distant, but alive and dynamic. Spiral galaxies twisting, colliding galaxies merging, and light bent and magnified by invisible dark matter, all revealed in stunning infrared clarity. Stellar nurseries, the birthplaces of stars. Webb's infrared vision pierced through cosmic dust to reveal star-forming regions that had been hidden from Hubble. In the Carina Nebula, Webb exposed vast cosmic cliffs of gas and dust, sculpted by the radiation of newborn stars. What looked like a wall of smoke and visible light became a vibrant landscape of formation, destruction, and rebirth. In the legendary Pillars of Creation, Webb unveiled dense knots of gas collapsing into new stars, showing the very process of stellar birth in unprecedented detail. These images were not just beautiful. They provided scientists with critical data on how stars and planetary systems form, evolve, and recycle matter back into the galaxy. Exoplanets, alien worlds unveiled. Perhaps Webb's most groundbreaking achievements are in the study of exoplanets, planets orbiting stars beyond our solar system. Within its first year, JWST delivered detailed spectra of exoplanet atmospheres. On WASP-96b, a hot gas giant, Webb detected water vapor, proving its method works. On other exoplanets, Webb identified carbon dioxide and methane, molecules crucial for understanding planetary chemistry. These are not just data points. They are the first steps toward identifying worlds that could support life. For the first time in history, we can analyze the skies of distant planets and ask, could life exist there? Biosignatures. The ultimate question, the holy grail of exoplanet science, is detecting biosignatures, chemical combinations that cannot easily be explained without biology. On Earth, oxygen, methane, and water coexist because life constantly replenishes them. Finding a similar mix on another world would be a game-changer. Webb's ability to detect faint absorption lines in starlight passing through planetary atmospheres makes it the best tool humanity has ever had in this quest. While JWST may not give us a final answer, it is preparing the ground for the day when we finally discover evidence of life beyond Earth. Beyond Exoplanets, mapping the invisible web also helps unravel cosmic mysteries beyond planets and stars. Using gravitational lensing, where massive galaxy clusters bend light from objects behind them, JWST has observed galaxies so distant and faint that they would otherwise be invisible. By studying how light bends, Webb indirectly maps dark matter, the mysterious substance that makes up most of the universe's mass dot. Combined with measurements of galaxy expansion, Webb also contributes to the ongoing investigation of dark energy, the force driving the acceleration of the universe's expansion. Humanity's place in the cosmos, every Webb discovery, from newborn stars to alien atmospheres, reminds us that the universe is not static, but constantly evolving. For the first time, we are not just looking at the cosmos, we are reading its story, chapter by chapter, through the faint light that has traveled billions of years to reach us. The fragile lifespan of a giant, for all its power, JWST is not eternal. Its orbit at Lagrange point 2 is stable, but the telescope relies on small thrusters to maintain its precise position. These thrusters consume fuel, and once it runs out, estimated after 15 to 20 years, Webb will slowly drift away, ending its mission. Unlike Hubble, JWST cannot be serviced by astronauts. It is too far, 1.5 million kilometers from Earth, 4 times farther than the Moon. Every system had to be designed to last, with redundancy built into every critical component. But one day the telescope will inevitably fall silent. Collaboration across the spectrum, JWST does not work alone. Its discoveries are magnified by collaboration with other observatories. Hubble, still operational, continues to study visible and ultraviolet light. Together, Hubble and Webb provide a panoramic view of the cosmos. Chandra X-ray Observatory reveals high-energy events, black hole accretion, supernova remnants complementing Webb's infrared vision. Ground-based giants like the Very Large Telescope, VLT, and upcoming Extremely Large Telescope, ELT, add further detail with adaptive optics and massive light-gathering power. This teamwork creates a multi-wavelength symphony, where each instrument plays its part to unlock the full story of the universe. Webb's legacy and future successors, even before JWST was launched, astronomers were dreaming of the next generation of telescopes. Webb is a stepping stone. The Nancy Grace Roman telescope will map dark energy and search for exoplanets with an enormous wide-field view. Levoir and Habex, still on the drawing board, aim to directly image Earth-like planets and search for life. The Origins Space Telescope could extend infrared exploration even further. Webb is not the end, it is the beginning of a new era. It shows what is possible and paves the way for even more ambitious missions. The cultural and human impact, JWST, is more than a machine. It is a story of human cooperation. Thousands of scientists and engineers from NASA, ESA, and the Canadian Space Agency worked for decades to make it real. It cost over $10 billion, faced delays, failures, and political pressure. But in the end, it launched flawlessly and unfolded in space like a golden origami flower. Its images, glowing nebulae, dancing galaxies, and alien atmospheres have inspired millions of people worldwide. For children, students, and dreamers, Webb is proof that humanity can build something extraordinary to explore the unknown. The ultimate questions, JWST's discoveries, force us to confront the biggest questions. How did the first stars and galaxies ignite from the darkness of the early universe? What is the nature of dark matter and dark energy? Are we alone in the cosmos, or is life a universal phenomenon? Every photon Webb captures is a piece of an ancient puzzle. Together, they may show us not only where we come from, but where we are going. Closing thought, the James Webb Space Telescope is humanity's greatest eye in space. It looks back over 13 billion years, yet also looks forward to a future where we may one day find other worlds like ours. It is a bridge between the past and the future, between mystery and discovery, between wonder and understanding. And as long as its golden mirrors reflect the faint light of distant galaxies, JWST will remind us that the universe is vast, beautiful, and waiting to be explored.